In this video, I'm going to use the portal method to find the approximate axial force, shear, and moment diagrams for this sample two-story building frame. So the portal method is an approximate method in order to solve an indeterminate structure. So in this case, the portal method uses a number of assumptions in order to simplify an indeterminate structure and make it into a determinate structure so that we can solve for all the axial moment and shear forces using nothing but equilibrium. And we do that by adding pins, hinges to the structure at points where we assume there's going to be zero moment, and also by assuming values for some of the horizontal shear forces at the bases of the columns. So to start, we will outline our assumptions. So here's the structure that we're starting with. It's two-story, two-bay, simple portal frame where the left portal is a little bit wider than the right portal. And we have two lateral loads, and we're asked to find all the axial moment and shear diagrams. So first, let's look at what the assumed structure is going to look like. So here's our structure with all of the assumptions that we're making in order to make this a determinate system. So first of all, we add hinges at the centers, mid-span or mid-height of all of the beams and columns in our structure. These are the locations where, due to a lateral load, we assume that there's going to be zero moment. We'll see what that looks like. And then at the base, we assume that the interior columns take double the shear of the exterior columns. So usually these interior columns typically are stockier because they carry more gravity load. So they also are generally stiffer as well. And when you have elements in parallel, the stiffer elements tend to take more load. So since the center column is stiffer, we assume that it has double of the shear of the exterior column. And these are the fundamental assumptions that underlie the portal method of analysis for building frames. So I've added all these hinges. Of course, there are also some unknown vertical loads at the column bases, and there are also some unknown moments here that we'll have to find out. Okay. So in order to do our portal method analysis, the first step is we have to actually find out what these shear forces are. And so we use the portal method. And in order to do that, we're basically just going to use a horizontal equilibrium. So at the base, what we have for our horizontal equilibrium, sum fx equals 0, we have 67.5 and 112.5, which are then resisted by these unknown horizontal reaction forces, which constitute shear in the columns. So first thing we have to do is find the total shear at the base that these reactions are resisting. So that just equals the sum of the horizontal external loads on the structure, which is 180. And then we do the same thing for the second story. So for the portal frame method, we have to do this this kind of thing where we find the shears in the columns. We have to do it at the base and then for each story above in order for us to get enough known forces in order to solve using equilibrium. So now that we know these values, we're going to find the force at the base. And using that horizontal equilibrium, sum fx equals 0, we get 4f, which is the total for all the shear at the base of these columns, equals the total base shear, which is 67.5 plus 112.5. Then we get that each f here is 45. So this one is going to be 45, this one is going to be 90, and this one's going to be 45. Then we do the same thing for the second story. And so if we were to make the cut at this location here, the second story, then our total shear that would act across all of these columns is just this 67.5. It's going to be split in the same way with double on the interior and single on the exteriors. And then we get 16.88. So the shear here is 16.88, the shear here is twice 16.88, and here is 16.88 alone. So then once we've found those column shears, then we've done basically all of the conceptual work that goes into the portal frame analysis. And from here, everything is basically just a simple determinate analysis where we have to find all of the rest of the unknowns. And it's best to go about this in a somewhat symptomatic way. So I'm going to start with the second story. With these questions, it's a good idea to start at the top of the building and work your way down. So start at the second story. So if I cut the second story off at the hinge location, so I'm cutting right here at the hinge, and I show the whole system as a free body diagram, then I get something that looks like this. So I have the horizontal shears that I calculated up here using the portal method, so the inner one is double the outer ones. We also have some vertical loads on these hinge locations, which are unknown right now, and this is the external load that's pushing the system over. Now, why do we want to cut it at the hinge? Well, the simple reason is that if we cut it at the hinge, where we know the moments are assumed to be 0, then we've eliminated those from our equilibrium. So we've eliminated those moments from our equilibrium equations, which means that it's going to be much more tractable problem to solve. So no moments because of hinge. So when we're doing our different equilibriums to solve for the forces in all the members after we've found those shears, we always want to cut at the hinges. And in fact, now when I want to do the full analysis, I'm going to cut at all the hinges, so I'm going to split this into 3 different pieces. So now I've split it up. So now I can do an equilibrium on each one. I've put the dimensions on here. These dimensions were just taken from the general structure. So you remember that the left bay is wider than the right bay, and down to the hinge is half the height, so it's 3.6 divided by 2, which is 1.8. So now I'm just going to add all of the known forces. Okay, so these are the same forces that we had above when I showed the entire cut. Okay, so now starting with one end of these, it doesn't really matter which end, now I'm going to go through and solve for all of the unknowns. So remember, we have a horizontal and a vertical unknown at every pin location, but we don't have any moments, because since there's a hinge there, we know that the moment at the hinge has to equal 0. So for this right piece here, I have to solve for 3 unknowns, the vertical here, and the vertical and horizontal here. So in order to start that process, and I'm not going to do this explicitly, but I will number the order. So these ones are number 1 because they were in the first step, which was the knowns. So the first one I'm going to do is sum of moments about this pin, okay, here, and then to find this vertical reaction. So I'm going to get that this is 13.5. Okay, so I'll number that 2. Okay, and now, so this one was from sum of moments. Then this one here, I'm going to use the horizontal equilibrium first in order to find the force, and this one is 50.6, so that's 3. And then I use the vertical equilibrium now to find this force, which is, since there's only one other vertical force, this is going to be 13.5, and that's number 4. Now you have to be very careful when you're doing this to keep track of the proper directions. So you want to actually draw these in the correct direction when you're putting them on. You don't want to, I mean, maybe when you do your analysis you can assume a direction, and then if you get a negative, you know it's in the opposite direction of the direction that you originally assumed. But when you draw it on the diagram, you want to get it in the right direction, because the directions are going to be very important, and because we have to carry those directions over to other parts of the system. For example, now we know that all of these are in the correct direction because I paid attention when I was doing the analysis. So this one is down, this one is up. Now when I transfer that load over to the next piece, okay, since this is a hinge that I've cut through, now we know that the forces have to be equal and opposite on either side of the hinge. So since this one goes up, 13.5, then we know that there has to be a 13.5 here down, okay, and that's still 4, so that's the same step. And then this one has to be 50.6 to the left, since this one was to the right, and that's also 3. So you have to go equal and opposite forces on either side of the pin, and that's how you always are carrying over. Also, the order that I do these in is not necessarily the only order. For example, now that I'm doing this piece here, I have 3 unknowns, a vertical at this joint and a vertical and horizontal at the left joint. Okay, so I could do these in a number of different directions. So I have horizontal ones at these 2, so if I do a horizontal equilibrium, I can go straight to this force, which turns out to be 16.8. Okay, and I can say that's number 5. You don't have to put these numbers, I'm just putting these for educational sake. Or instead of finding this one first, I could have done a moment equilibrium about this point and then found this one directly here. So if I do moment equilibrium here, these two are known. This one doesn't actually come into it since it's in line with the point. This one is known, and the only unknown is the vertical reaction here, which turns out to be 3.3. And I'll call that 6. Okay, and then this last one comes out of vertical equilibrium, which we get 10.2. Now, if you have trouble following the equilibrium steps that I'm going through, you probably want to just start with it fresh and try to figure it out for yourself, just with the knowledge that you know that you will be able to solve it in one way or another. So there is some way to use the 3 equilibrium equations to find the unknowns, as long as you only have 3 unknowns in each step, which is generally the case after we carry over, right? So this one started out with 5 unknowns, but then once we solved the right one, which had 3, we could carry over 2, right, which carried over to the other side, and that left us with only 3 unknowns on this one, okay? And then so now that I've done these, I can carry these over, equal and opposite directions. If you remember, 16.85. This one is now down 10.2, number 7. And then the only unknown here is the vertical at this joint, which is 10.2. And I'll call that number 8. So now we found all of the unknowns for the second story, the top of the second story of the structure. And now that we've done that, we have to go down to the first story and repeat the entire process. So now that I'm down at the first story, again, I have cut it only at the hinge location. So I haven't gone all the way down to the base. This is the hinge in the middle of the second story, and this is the hinge in the middle of the third story. And now the first thing that I'm going to do is to carry over my forces from the story above. So you have to remember again that these are in equal and opposite direction. So these ones are all of the carryovers. So this one was up, so this one is down, this one is to the right, therefore this one is to the left. So remember, this is one side of the joint, and this is the other side of that same joint. So we're just carrying over the forces that we calculated for the story above. And then you can't forget to add the external force onto here. If you don't add that, then your whole equilibrium will be thrown off. And then at the bottom, we're going to add the story shears that we calculated for the portal frame at the beginning, which is 45, 90, 45. So you'll recall that's this part right over here. So we found the story shears at the base, so that means that the shear at this hinge is also equal to this force. So it's 45 at the left, twice 45 in the middle, and then 45 at the right. And then we still have these unknown vertical forces, which we don't know the force or the direction. So again, I'm going to split this up at all of the hinge locations, so I'm going to turn this into 3 pieces. So this situation looks a little bit more complicated than it was above, but actually we're still going to only be working with the 3 unknowns that we're used to in order to find the equilibrium. And of course this is the advantage of the portal method. So again, I'm going to apply all of the known forces. Okay, so these are all of the known forces from the story above, and these are the base shears that we got from the portal method. And now we're going to go through again. So you see here on the right, we have 3 unknowns, 2 at this joint and 1 at this joint. So in order to find the vertical unknown at this location, at the lower right here, we're going to take moments about this pin right here, right? So, you know, it's best if you can get used to doing this process without having to write it all out at once. But if you have to write it out, or if you want to write it out on a scrap piece of paper just so that you know that you get the directions right, then that's not such a bad idea. You know, but really we have to do this so many times in this process, you know, finding the moment equilibrium, finding the vertical in horizontal equilibrium, that you really want to get to a point where you're very comfortable with doing these kind of pseudo in your head, you know. So you can go a moment about this point, keeping track of the directions of the moment. These are counterclockwise, they're positive. This is counterclockwise also, so it's positive. So that you know that you have to have an anti-clockwise or counterclockwise force here of 63.0 just out of the moment equilibrium, and you know, keeping track of all of these dimensions and everything in order to find that force. So this is number 2. So again, do this yourself as well to convince yourself that you know what you're doing. So this is vertical equilibrium now, right? So that's number 3. and then horizontal equilibrium to get this one, 84.4. That's number 4 in the way that I've done it. And again, you don't have to do it in the same order that I do it, as long as your order makes sense. So then we're going to carry over these forces, equal and opposite direction. Okay, that's 3. This one must go to the right now, so that's 4. Okay, and so now, okay, we have an option of what we want to do, but maybe this is the easiest one. So if I put my moment location here, right, then I can do all of these. And now, I have to add up 1, 2, 3, 4 moments that are resisted by the vertical force at this location. And again, trying to keep track of it all. 15.6. So this is number 5. Oh, sorry, I didn't write this number here. 84.4. And then again, vertical and horizontal equilibrium gets these. And again, remember to keep track of your directions. You have to know that all of these are in the correct directions and that they're drawn in the correct directions in order for you to properly keep track of it. I would not do these all in one direction and then put negative signs. You're going to get so confused. So I would advise you for these kind of problems to just draw these arrows in the correct directions. So we're going to carry over these forces, 37.2, it's number 6, and 28.6, which is number 7. And then here we only have one unknown that we can get easily using vertical equilibrium. That's 47.4. And this is number 8. Now just a note about accuracy here. I'm only doing these to 3 or 4 significant figures. I'm not being terribly consistent here. But since this is an approximate method, the output moments and shears that we're getting are probably only good within probably best 20% or so. So, I'm not too concerned about the fine, detailed accuracy of my numbers. I just want to keep them accurate enough so that I can add up all the equilibrium numbers at the end and make sure that I haven't forgotten anything or made a calculation mistake. So if I leave these too coarse and they're not accurate enough, then when I do my moment equilibrium at the end, I might not get close enough to 0 to satisfy myself. So the last step here is to look at the base, which is below the location of the hinges in the first story. So if we go all the way back up, we see we have a hinge here, and there's a little bit that's below that hinge. So I'm just going to draw it for the sake of completeness, and it'll help us when we're calculating our moments. So we have 3 columns that look like this, and we have a height. I'll do this very quickly. So this is 1.8, which is half the height of the column. So I'll draw these hinges here. And then we can just carry over the moments, the horizontal and vertical forces from above. Again, in the equal and opposite directions. 15.6 and 63.0. 45, 90, 45. Now you can notice now from here we can automatically calculate the reactions at the very base of the column. So we know that we have horizontal shear reaction, right? Okay, from horizontal equilibrium, right? 45. We know that we have vertical force reaction, which directly counterbalances these. Okay, 15.6 and 47.4. Okay, but also since this is a fixed end, we have a moment reaction, right? So there's a moment that goes like this, right? And what's the moment here? Well, if we take a moment equilibrium about the bottom of the column here, we have 45 times the height, 1.8. And for this column, that gives us 81. So we can see how we can go from these different structures in order to calculate the moment. So for this case, okay, we have a moment that looks like this, and this value is 90 times 1.8, right, which is 162. And this one likewise is also 81. Okay, so this is kind of the process that we're going to go through to calculate our moments throughout the structure on the moment diagrams. So say we wanted to find the moment at the left side of this beam, right? So we can actually cut this beam here, and we know that the horizontal is 28.6. We know that the vertical, which is the shear, is 37.2 up on the left side. But we also know that the moment is going to be equal to 37.2 times this distance, 3. And in this case, it's going to be 111.6, and we're going to draw that on the moment diagram. So instead of doing that individual for each piece, I'd like to draw out the full moment diagram. And so in order to do that for each little piece here, which kind of acts like a cantilever in the structure, okay, since we have a horizontal and vertical reaction and kind of a fixed node at the root, right? Then we have 37.2 times 3 is going to give us the moment here. 33.8 times 1.8 is going to give us the moment here, etc., etc., etc. So let's start drawing these things. I'm going to start by drawing the axial force diagram. And so you'll have to excuse how ugly this is going to look just from drawing it on the computer here. But so I'm going to draw axial forces for each member. Okay, so if we want to look at this member, for example, the left column, we can look either at this lower piece of the column or the upper piece of the column. The axial force is not going to change in between those two. So you can see that we've made this cut here, and in the middle of the column we have 47.4, and that's creating a compression force in the column. You see above it's also creating a compression force in that column, 47.4, right, which is reacted by this column above plus the shear in the beam, right? So these two add up to 47.4, but in that column it's 47.4 in compression. So what I'm going to do is I'm going to draw 47.4. So I'm just going to give it some width here. I'm going to draw that on my diagram. Okay, and then sometimes I'll draw some arrows, some lines, just to show kind of which column it's attached to, and this is 47.4, and I'm going to put a little C just to be clear that that's in compression. Well, what about this column here? Well, this column has 15.6 in compression. Same above, right? 15.6 in compression. So here I'm going to draw 15.6, which is certainly smaller than the 47.4. Okay, you're just going to have to imagine that these are straight lines. So this is 15.6, also in compression. Okay, what about the beams? Here, I'll draw the beams in red. So this first story beam here, okay, right? This is the second story up here. So let's look at the first story beam. Okay, we can see that we have 28.6, and that's pushing towards the beam. So it's putting this beam into compression, right? On both sides, it's putting the beam into compression. So we know that this beam has 28.6 compression. I'm going to draw the compression. In general, I'm drawing compression on the right side of a member and on the bottom of a member, and tension on the left or the top. So for this one, it's compression 28.6. So I'm going to draw it below the member. Okay. Now, it would really be ideal to do this with some sort of ruler. Okay, but again, just imagine these are straight lines. 28.6 in compression. Okay, and then I'm going to do that for the rest. And we get this situation. So you see the columns on the left and in the middle are in compression. The one on the right is in tension, which we expect because remember our loads look like this. So they want to twist this section, so it's got to push up on the left and it's got to pull down on the right. It wants to uplift at this column, right? So that's where this tension comes from. And then I've drawn tension on the left and compression on the right. And all of the beams are in compression. Okay, so let's go on and draw the shear diagram and see how to do that. So shear. Okay, so maybe in contrast to what I've been doing before, I was going shear, kind of positive shear I was always doing on the outside of the frame. Well, that's not really appropriate for a frame like this. So I'm going to put positive shear on the top and positive shear on the left. So it's on the left for all of these columns and it's on the top for all of these beams. So you remember positive shear looks like this, right? Up on the left, bottom on the right. Okay, so I'm going to look for this bottom column, for example. So for this column, we have, if we're looking at shear as the top, so we have down on the left and up on the right. So this is negative shear. And the value of that shear is 45, right? And it's constant over the height of that column, right? So it's 45 here, 45 here. We have 45 for the top part of the first story column, and the other 45 comes from a combination of the shear in the column above and the axial load in the beam. So these two add up to 45. So there's kind of an effective right? Shear force here of 45. So let's draw that 45. Now, which side you draw the shear diagram on is not totally critically important. What's more important is that you draw the moment diagram consistently on the correct side. So there's one column, 45. For the top one, you can see it's 16.88, right? 16.88, 16.88 for the top column, and that's also negative, so it's going to be on the inside, so I'll draw that one too. Okay, this is 16.88. Okay, and then if we want to look at one beam, for example, let's look at the first story beam here. So this one is 37.2, and this is also constant shear. So on the right side at this pin, we have 37.2 down. On the left side, we have the combination of the two axial loads in the columns, which provides a net 37.2 up at the left. So it's up at the left, down at the right. So this is a positive shear. So I'm going to draw it above the beam, and the value is 37.2. Obviously, these are only roughly to scale. So I'm going to draw the rest. And again, just imagine that all of these are straight lines, and it's approximately to scale. So now, for the main course, we have the moment. And these numbers will be in kilonewtons and meters. It's important to put your unit if you're not putting the units on the diagram itself. So I'm drawing this one a little bit bigger, so hopefully we have a little bit more space for all the moments. Okay, so let's look at moments in the column. So now we have pins here, right? So we know that the moments are going to be 0 at the centers of all of the columns, okay, because we've added those hinges. And this was the assumption that we made at the beginning of the portal method analysis in order to allow us to solve this indeterminate structure as if it was determinate. So if I were to just look at the moment diagram for just the lower part of this column, right, I have 45 pulling on the top of a cantilever here. So we remember the moment was 45 times the height, which is 1.8, and that came out to 81. And the compression side of that is the left, right? So I'm going to draw all the moments on the compression side, and you can draw them on the tension side if you like, but you just have to make sure to be consistent. So if we were to draw just the moment in this column below the hinge, we know that we would get a triangular moment distribution because it's got to be 0 at the hinge and it's 81 at the base. Now if we look at the top part of this column here, okay, we have 45 again, and this acts as a cantilever as well. There's no moment at the hinge, and this is times 1.8. So 45 times 1.8 is again going to be 81. So we have a continuous slope here because this is half height, and this comes out to 81 like this. And so this is the moment in this first column. And this is going to be the general case that we're going to have the same moment at one end as we have at the other end. And that's a consequence of the fact that this hinge that we've created is at the middle of the column. So we only have to do this moment calculation for one end. So let's do the second story column now. Now we have 16.8 times this height, which is 1.8. And that comes out to, oh, sorry. Yeah. And that comes out to 30.4. And again, the compression side is on the left. So it's going to look like this. This is linear. This is 30.4. And this up here is the same. And that's 30.4. Okay, now let's do this beam here so that we can see that we have compatible moments around the corner. So the top beam, okay, is 10.2 times 3 meters to find the moment at the root here. So it's 10.2 times 3, and that equals also to 30.6. Okay, and this comes like this. Okay, this actually has to cross at the hinge at the center. Okay, and this is equal to 30.6. Now this is not exactly equal, but again, that's due to our round-off error, so it's close enough. And we have compatibility of this moment around the corner. So the compression side is always on the inside, which if you'll remember from our displaced shapes And from all of our other analyses and determinant structures, this has to be the case all the time. Now, what about if I do this hinge? So I'm going to put all the moments for the members around this hinge on. Okay, so now I put all of the moments that are around this particular joint on here, and I did the same thing. So I had the shear in this column times half the height, right? And I got 60.8, and then I had the shear in this beam times half the width, which was 30.4. And now all of these actually add up together. So if you draw a little diagram of this joint, okay, and now I'm drawing the loads that are at the ends of these members, okay, so it's tension to compression, the moment diagrams. So I'm drawing the forces that are on the members themselves, not on the joints, okay, so these are the moments on the members, okay. Then I have something that looks like this, right, where the arrows go from the tension side to the compression side, right? Okay, so now this is 30.6, this is 30.4, and this is 60.8, and I have 2 counterclockwise moments and 1 clockwise moment, and so the counterclockwise moments and the clockwise moment cancel out, and that's what we expect to have moment equilibrium about that joint. Okay, so if I was actually drawing the joint itself, right, then I would draw the opposite forces. So this one would be clockwise, this one would also be clockwise, and this one would be sorry, let's try that again. So now if I were to draw those on the other side of the joint, then this one would be counterclockwise, right? So I'm just drawing the opposite of what it was above. This one would be counterclockwise, and then this one would be clockwise, and those would all cancel out. Okay, good. So that's the equilibrium about this joint here, in case something weird happened with the video and I missed that. So this was 30.6, this is 30.4, and this is 60.8. So this is just another check that all of these moments do indeed add up properly, and the sum of all the moments about each joint should be 0. So let's draw the rest of the moments in here. Okay, and we end up getting all of these moments shown here. Again, all of these are straight lines. These are all triangular, and if I look at the equilibrium about the center joint here, you'll see that this 60.8 causes a counterclockwise rotation about the center joint. Same with the 162.2 causes a counterclockwise rotation about the center joint, and then 111.6 and 111.4, right? So 111.6 plus 111.6 minus 60.8 minus 162 equals approximately 0. So we know that that makes sense. Okay, now one last thing that we can do to convince ourselves that what we've done is reasonable is to check our overall equilibrium. So I'm just going to put all of the forces onto the structure. Okay, so these are all of the external forces on our structure. These are the applied forces, and these are the forces at the base. So 63, 15.6, and 47.4 are the axial loads, drawn in the correct directions, because these ones are compression, this one is tension. These are our base shears, which were actually assumed at the beginning of the portal method, and these are the moments in the correct directions that we calculated on the moment diagrams here. So right, the arrows go tension to compression side to compression side. We've drawn the moments on the compression side. So now I can check, does our sum of the moments equal 0? Okay, and I'll do moments about A. So if you recall, this is A, this is B, this is C, for example. Okay, so then if I do that sum of moments, then you see we get moments due to the external loads, moments due to the axial loads, right? This one is negative because it's clockwise, this one is positive because it's counterclockwise, and then each moment at the base of the columns are just added on here. So these are all clockwise moments, so they're negative, and you see we get negative 0.9, which is pretty close to 0. So then we check. This is not exactly 0 because we've lost some accuracy in the number of decimal places that we've assumed along the way. And we can do the same thing for Fy. Oops. Fy equals 0, question mark, right? And then we get 47.4 plus 15.6 minus 63 equals 0. Check. And so now that gives us some confidence that the analysis that we've done is correct. If you're doing this on an exam, for example, and you have some extra time, this is something that's really good to do. So at least if you get to this point and you find that your equilibrium doesn't make sense, then at least you can say here, well, it looks like I've made a mistake somewhere along the way. I don't have time to fix it, but I recognize that there's a problem. And that's the full Portal method. And check out a additional video that I'm going to do right after that's going to go through the exact same structure using the cantilever method instead.